Welcome to Tuesday, guys, and we're going to look at more complicated questions to do with latent heat and just, I suppose, general heat transfer. So the questions today we're going to talk about are very similar to the questions that we dealt with before, where we had water changing temperature and it was sitting inside a container. So just to recap on this, one thing is definitely assumed here, and that is that the liquid and the container are at the same temperature. But what I want you also to think about is what happens when you have liquid that is poured into a container. So I suppose a good example here would be a container of 80-degree water up here, okay? And you're pouring that into a cup. Now your cup is at room temperature, it's at 20 degrees, and you pour that in, it's nice and hot, and you let it sit. And the both of the cup and the water come to the same temperature because obviously they're in contact, so they are. But the water is now, or your coffee, or we'll go with coffee. Coffee is now at 68 degrees instead of the 80 degrees that it went in. Where is that temperature gone to? Or where is that heat energy gone to, I should say? Well, if you look at the cup, that temperature has risen from 20 degrees up to 68 degrees. So a couple of simple questions to ask are, what has lost heat energy here and what has gained heat energy? So both the water and the cup have changed temperatures. One has risen and one has dropped in temperature. So from that, it's, I suppose, relatively straightforward to think about what has lost heat energy. So the object that has lost heat energy in this case is going to be the coffee. Well, we'll just stick with water for this. Make it easy, because that's what we're going to be dealing with in the rest of the question. So the water here has lost the heat energy, but that exact amount of heat energy that it lost, the cup gained. So that is what we're basing our calculations on. Now, in real life, that's not always the situation. You're going to lose heat energy to the air, and the cup might heat up the table a little bit, but we're going to look at just simple situations where the heat is not lost. There is no heat transfer to anything outside. So in that scenario, and in all the questions that you are going to deal with, you always take that the heat lost by one body or two bodies or however amount of bodies that are cooling down is the heat gained by the body that is heating up. Okay? In this case, you had the water cooling down, which lost the heat, and we could calculate, if we knew the mass of the water, we could calculate how much heat energy it lost from the formula Q is equal to mc delta theta. Okay? The water went from 80 down to 68 degrees, so it dropped by 12 degrees. So that's our change in temperature. The specific heat capacity, and this is why I wanted to keep it with water, is 4180. Again, you would be given this in the question, and the mass, we don't know what the mass is, but if you know, if you're given that in the question, you put that in there, and there you have how much heat energy the water has lost, which is also the heat energy that the cup has gained. So you might be able to work out the mass of the cup from this. You might be able to work out the heat capacity, specific heat capacity of the cup from this. So there's lots that you can do here. Now, what we are going to look at today is we're going to look at questions that deal with that. So let's look at a question from your book then. This is page 112 in the textbook. So what they are talking about here is adding steam into water that sits in a copper calorimeter. So the steam obviously is going to lose the heat. So we'll list it out here. What's losing the heat and what's gaining the heat? So you have your copper calorimeter here, you have the water sitting inside it, and then you have a little pipe, whatever way you're going to get your steam into it, and you add in. Now, this actually is going to be, this is exactly the same as one of the experiments that we're going to do. So that's why I am getting you to do these questions today. They might seem a little bit tricky at the start, but the key part of this is following the method that I've given you here. Okay. First thing you do is look at what is losing heat or what's gaining heat. So I'm starting with what's losing heat, and that's the steam. The steam, first thing, the two ways that it loses heat is, first of all, by changing state. So it is going from steam at 100 degrees to water at 100 degrees. Now, it is giving out specific latent heat of vaporization at that stage. So I'll just put a little ml in here to show that that is how I would calculate how much heat energy it is giving out here. And then when it gets to water at 100 degrees, it then obviously is in contact with water that is at a lower temperature around it. So it's going to continue giving heat energy out to the water and the calorimeter, and it's going to change temperature. And it will come to the final temperature, which they tell you in here. And they're also saying that no heat is lost to the environment. The water changes temperature from 7.9 to 19.8. Now, the water changes temperature. The calorimeter also changes temperature because it is in contact. But they don't tell you that in the question. You have to assume that. So that increase in temperature is coming from the steam. That's where the energy is coming from. Sorry, my formula here is mc delta theta. Okay. So what's gaining heat? The water, and again the amount of heat, mc delta theta, right? And the calorimeter, how much heat does that gain? Well, again, mc delta theta. So the mass of the calorimeter, specific heat capacity of the calorimeter, and the change in temperature of the calorimeter. So that's first step that I would do. Set out what's losing heat and what's gaining heat. Next step, put out your masses and the temperature changes. So they're telling you here in this question, 1.4 grams of steam. So the mass of the steam here, change that into kilograms, 0.0014. Okay, so you're dividing by 1,000. The 62 grams of water, okay, so that's my water that's inside in the container. Again, change that to kilograms. The calorimeter's mass is 35 grams, 0.035 kilograms. So your masses are laid out nicely here. And then any change in temperatures that you can put in. So they gave you that the steam went in at 100 degrees. So the only place that it doesn't have to come down in temperature to 100 degrees, the first thing that it's going to do is change state. And then it's going to finish. And the temperature it's going to finish at is this temperature here. So you have to read the question carefully to get this. So you can work out the temperature change of the steam. Starts at 100 degrees, water at 100 degrees, and finishes at water at 19.8 degrees. And your temperature change of the calorimeter and the other water is fairly much more straightforward, 19.8 minus 7.9. So now you have everything that you need to go ahead and do the question. So heat lost, and I always encourage people to start off the questions like this. Heat lost equals heat gained. Now, you can start off with heat gained equal heat lost. It really doesn't make any difference. But go back up here with what is losing heat, your steam. How, what are the steps that it's losing the heat, or how much is it losing? So the first step is that it is changing state. So you are going to put down ml here, and now do out the formula first. ml, and then it is giving out heat in the form of mc delta theta. Okay. What's gaining heat? The calorimeter. The water, mc delta theta, and the calorimeter, mc delta theta. Now, lots of places will put little subscripts in here, and they will put subscripts in to show you that you are talking about steam over here. So the mass of the steam times latent heat of vaporization. Mass of the steam. This is the mass of the water. This is the mass of the calorimeter. The specific heat capacity of water, specific heat capacity of your calorimeter. Change in temperature of your water, change in temperature of your calorimeter. So now watch this here. Don't put S over here because this is water. So it's the mass of the steam, but it's the specific heat capacity of water. And then the change in temperature of your water over here. So that, I would say to do that, to be honest. It definitely looks a lot better in your Leaving Cert if you have those subscripts in there. Now I know this is an awful lot of setting out of a question before you haven't even done a calculation, but that's the key thing here. Once you get it set up, then you'll absolutely fly through it. And the other important thing is there are marks going for just this. If you don't do any calculations, you could get as much as half marks for a question for just writing those formulas down. Now, an important part. What are they asking you in the question? And usually I would deal with this at the very beginning. Got a little bit lost. The specific latent heat of vaporization. That's what you don't know in this. I don't have them listed here, but in your book they give you the specific latent heat of vaporization. Sorry, don't. They give you the specific heat capacity of water and of is it the copper in the calorimeter? Yeah. So I'm just going to write these out here, and what I would suggest that you do is pause the video at this point, take that down and fill in those figures yourself. Okay? In fact, I would suggest, if you felt confident enough with it, is not only filling in those figures but actually completing this and working out what L is. Because remember, you know everything else here except for L. So I'm going to pause this, I'll write it out, and we'll come back into it. So you guys need to pause at this point and fill in the figures. Okay, so hopefully this is what you got. Now I've color coded this to make it a little bit easier to follow. These are very daunting when you do them first, definitely. The key to this is breaking it down into, and I always think of these as little packets of MC delta theta or ML. Okay, it's going to be one or the other. So you then have to work out what each section is. Okay, so you're going to multiply out the purple section, the green section, the blue section, and basically bring everything you know to the right hand side. And you are going to end up with something that looks like this. 0.0014 L is equal to something. Okay, so off you go and try that. So that's what you're going to end up with, 2789.62. Divide then by 0.0014, and that gives you 1.99 by 10 to the 6 joules per kilogram. So what I want you to do is, in your books, you have question 7 and question 8 that are similar-ish enough. 7 is almost identical, except you're using ice in this case, and question 8 then. I want you to have a go at those. Okay, thanks guys.